don't think so, no. Here's your...
Sure.
Hey everyone, this is Jacob Levy with Meta Learning Online Dynamics Model Adaptation and Off-Road Autonomous Driving.
Yeah.
That's all I got. All right.
All right, good morning, everyone. So I'm going to tell you about our work, Meta Learning Online Dynamics Model Adaptation in Off-Road Autonomous Driving. So yeah, when you have varying terrain types in off-road driving, like driving on the beach, through vegetation, through sand, and varying terrain conditions like wetness, deformability, these can drastically alter your vehicle dynamics. And if you're doing model-based control with your dynamics model and you have this varying terrain, you want to be able to adapt to it. And so you want to adapt to it online. And the question is, what's the best way to perform this adaptation? For us, we're using MPPI for control. And how it works is you randomly sample control sequences and roll them out on your dynamics model to generate trajectory samples. And you use this to determine an optimal trajectory forward. And in our case, we want to maximize the velocity of the car, keep the car in bounds, and minimize the risk of the car rolling over. And so for the last point, we'll assess, we have like a safety metric to determine if the car is at risk of rolling over, and we want to keep it below some threshold. So I just want to flash on the screen really quick the dynamics model that we're using. And the main part of it is the tire forces are coming from the Pisagya tire model. We have a neural net, LCM, and a feed-forward neural net that is issuing like residual corrections to the tire force model. Okay, so in traditional learning, let's just say F is this, you have an actual dynamics model like F actual, and you want to learn a parameterized version of this, and so you have these parameters phi that you're trying to learn, and you want to best approximate your real-world dynamics, and you just do gradient descent, and hopefully you come up with some set of parameters phi which are close to the optimal parameters phi star. Okay, so let's just pretend for a second that you have different like discrete dynamics models. So pretend maybe like F1 is dynamics driving through snow, F2 is like through sand, F3 is through like gravel or something. And let's just say they're separate dynamics. You have separate dynamics. And so if you take this approach and if you don't have enough model parameters, then you end up kind of like descending to a location in parameter space where you kind of just are like a best fit between your optimal parameters for each model. So something that meta learning lets you do is we want to like find the optimal parameters for each dynamics equation. So like let's just say that's what we want to do. These are like separate objectives, and then the meta learning objective is like, okay, how do we find the best starting parameters such that we can adapt to each of these dynamics in the future? And so kind of like what this looks visually is like, okay, we're gonna like find our self and parameter space where we're close enough to each of these points, and then we know we're gonna adapt in the future. What's the best way to get us to knowing that we're gonna adapt there in the future? Okay, so with that in mind, this is our approach. We have our learned model, and that's gonna that feeds into the rest of the physics-based model to generate dynamics predictions. And then we're going to take the last layer of the learned model and split it into an ensemble. And just for a minute, you can just imagine that each like layer in this ensemble or model in this ensemble, just imagine one is for like different terrain types. So one is for like gravel, one is for like snow or something. Okay, so when we're driving over the terrain, we're going to take a linear combination of the output of each model in the ensemble and weigh them by this parameter phi, and then add a bias to it. Okay, so then to do online adaptation, we formulated a Kalman filter, and the Kalman filter is, it's not estimating state. What it's estimating is a correction to the weighting, the ensemble weighting. So it's kind of online telling you take some from this model, take some from this model, and changing that weighting. So that's what we're doing online. Offline, we take our entire data set and we split it into different trajectory segments. And then for each segment, we take the beginning part of each trajectory and run it through the online adaptation procedure, and that gives us a new weighting of the models. So with this new dynamics model, adapted dynamics model, we make a prediction, and we take a loss on the prediction against the actual data. And then so when we do backpropagation, we're backpropagating through the dynamics prediction, and crucially, we're backpropagating through the online adaptation process. And so by doing that backpropagation, it allows us to meta-learn, or in other words, optimize the online adaptation procedure. So specifically what this means is that we learn the ensemble weighting, which you can think of as like the directions of adaptation. And something to point out is that initially I said imagine like one of them is for snow, one of them is for rocks, whatever. Since we don't have those labels, the meta-learning learns the best way to point these different models and given the data that we've seen. And then the other thing we're meta-learning is the Kalman filter parameters, which they ultimately govern the rate of adaptation. So how fast do we think we need to adapt in the future given the data that we've seen? And I think it's kind of good to appreciate the math behind the gradient when you do the backpropagation. And so if you call in here, like phi is the model parameters that we're learning offline, and then theta is the model parameters that the Kalman filter is adapting online. So in a traditional learning approach, if you just take the gradient with a loss with respect to parameters, I mean that's it. That's just the derivative. But when you look at the meta-learning part and you look at the adapted parameters, you get this extra term. And so the extra term is the derivative of the adapted parameters with respect to the model parameters. So it's telling you changing your model parameters, like how much does your adaptation change, and that informs the meta-learning aspect. So for training, we collected 9.5 hours of autonomous driving data through a diverse range of terrains. So up here you see vegetation and mud and steep slopes. We trained for 5 epochs without meta-learning, just to get a good initialization, and then we turn on the meta-learning and we train for 15 more epochs. So for real-world validation, we have this figure-8 type track, and we're going to compare against the baseline with no online adaptation, no meta-learning, and we're going to look at if the car stays in bounds and also if it exceeds the rollover safety threshold limit. So this is kind of what it looks like running with the baseline, and it's going to go out of bounds right here, and then I'm going to skip forward, I think. Okay, well, it basically ends up at the end taking the last turn a little wide, and has to perform a costly backup maneuver. And so yeah, so when we were running the baseline, the dynamics predictions weren't as good, and so MPPI was kind of having to overcorrect. And then so it's running smoother with the adaptation. And so here are the results. We ran 4 runs each with the baseline and 4 runs with meta adaptation. And if you look at the table at the top, it had the fastest completion times around the track, lowest prediction error. And then if you look at the baseline on the left, the blue paths that it took, if you look between the runs, it's kind of more erratic. And then if you look at the red spots, these are all the parts where it exceeded the rollover safety threshold. And then if you look at with meta-adaptation with our approach, the runs are more consistent, and it doesn't go out of bounds as much, and it doesn't exceed the rollover safety limit as much. And then we also did simulated experiments, and we procedurally generated 4 maps, and they're labeled like either shallow, dense, steep. So this is like how steep the hills are in the maps, and then also how dense obstacles are. And this is kind of what it looks like running in the simulator, and the top graph is the norm of the adapted parameters. So they start at 0 because there's we don't know what the correction is, and they online adapt. And then the bottom right graph is the model prediction error. So looking at the last 5 seconds, like compare where I am versus where I predicted I would be. And the blue curve is with the online adaptation. So you can see at the beginning of the graph that the red and the blue track each other because there's not any adaptation happening. And then as the model adapts, it corrects itself, and you'll see the blue curve is a lot below the red curve. And also something interesting to point out with running in simulation is that we did all of our training using only real world data. And so now we're taking this model trained only in the real world, deploying it in the simulator, which has completely different dynamics. And so we had to, the model had to adapt to the simulator. So it has to bridge a real to sim gap. And yeah, here's some of the results from the simulated experiments. And yeah, that's what I got. Any questions?
Thank you very much. We're moving up the tech tree. We've unlocked a second microphone. So does anybody have any questions from the audience? Question from the audience? All right, so what, oh, yeah, go for it.
So I was curious, like, did you do any analysis, or were you able to see whether, like, the different, like, ensemble methods, whether they are actually, like, learning parameters that kind of correspond to, like, distinct, like, environment types, I guess, from, like, the different things that you were training on?
Yeah, good question. Yeah, it would be interesting to see if it learned some sort of interpretation like that. But we didn't have labels, so there's no way to check that. But kind of the cool thing about this is, like, the meta learning allows it to not only, like, you don't want it to just segment different terrain like classes, like snow, sand, whatever. Like, it's picking out like other features which may be a little more rich that as humans we can't interpret. So
Thanks.
Any other questions from the audience? All right, so I have a question. So, we're all doing field robotics of some sort. So this whole, sim to real, real to sim, what are some of the big challenges that you saw with, dealing with either hardware or dealing with the software? What were some big challenges with that?
yeah, so in this case, there wasn't a jump, at least in my part of this, there wasn't a jump from sim to real. But I think from going from real to sim, I was actually surprised that it kind of just worked. I didn't have to do any tuning or anything. And so that gives me hope for, if we did this the other way around where we trained only in sim and wanted to jump to real, that that it would be able to adapt.
Great. Any other questions? Yeah. Can we just?
Hi, great talk. So I have one question about, so I've seen like in your real world experiments, mostly just one type of terrain and also in your simulation. So I'm wondering like, what if you're like facing a terrain with like varying semantics, like for example, it's a terrain of varying like grass, marble, rock, then does the model just kind of like adapts to each of them or, well, yeah.
Yeah. So I would, yeah, it definitely would have been great to test in, like, yeah, with terrain where there's many types like in the same area. But I will say that even within this one test location, like there's areas where it's a lot smoother, and areas where it's more rocky. There's like There's areas where there's like ditches. It was doing some adaptation to different like terrain dynamics, even within this one real world scenario. If you look at the paper, there's a graph of what the adapted parameters are doing, and it's if the terrain was completely uniform, then you would expect the parameters to just like converge, but instead you see them like kind of going all over the place.
Well, thank you.
All right, we've got time for one more question, and then we'll start the poster session.
Have you tried running this with adverse conditions like when it's rained, so it's muddy, or where you have soft soil dynamics to deal with, not just gravel?
Yeah, I would absolutely love to. But it gives me hope that the real to sim transfer was so good that when you do drastically alter the real world dynamics, that it would be able to adapt.
It'll be fun to see this in the muddy environment.
Yeah, I definitely agree.
All right, thank you very much. All right, so that is the end of the first part of the morning. So we're going to start the poster session. That is, do we know specifically where outside it is, or just outside Pung? So anyway, everyone with posters, you can go start setting those up on the boards, and we'll get the specifics on which boards. Thank you. That was really cool.
Do we know which boards? We reconvene at 10:30.
Thank you, Christian. Sorry, this is my first time doing this. We're going to come back here at about 10:25, and we'll start again at 10:30. Thank you.